OK, so now we're going to sort of go through different problems with VLIWs and different solutions to those problems. Sort of a top one on this list is a problem of hard to predict branches and how that can limit instruction level parallelism. So you just remove the branch. And we're going to call that predication. So we're actually going to add instructions to the hardware, which we're actually going to add two instructions here. So this is limited predication, but we're going to add two very simple instructions. And if you look at these instructions, they're very similar to the question mark colon or the select operator in C. So what does that operator do? If we have A equals, I don't know, C question mark D colon E, semicolon. What does this do? Well, it loads A. If C is true, it loads A with D. If C is false, it loads A with E. Well, you can think about actually doing this with some sort of if-then-else piece of code, which is pretty common. If A is less than B, so you can sort of put that here. X gets A versus X getting B. That's our select operator. Well, we can add two special instructions here for our limited predication. Move if 0, and move if not 0. Well, what does this do? Well, if this operand is equal to 0, then this RD gets RS, else, and that's all it does. That's all that instruction does. And the flip one here is it checks if it's not equal to 0. Why is this cool? Well, this allows us to transform control flow into a data instruction. So we taken a branch out. So if we look at this piece of code, if we were doing it with branches, set less than, we do a branch. So this computes our condition code flag here. Branch equals, and if it's the one way it branches here, if not, it jumps over it. So we have a bunch of control flow here. We have two control flow operations, the branch and the jump. When we add these instructions, we can basically do that if-then-else in an instruction. And basically every VLIW processor you're going to look at is going to have predication, or at least limited predication. This is not full predication. This is limited predication. We'll talk about full predication in a second. OK, so let's think about that for a second. We just took control flow. We turned it into something which is never going to take a branch mispredict. That sounds pretty cool, because branch mispredicts, were pretty bad. If we had a branch which was hard to predict, we didn't know with high probability if A was greater than B or not, we can just sort of stick this code sequence in here and just be done with it. And why this is really important for very long instruction-word processors is because whenever you take a branch mispredict, you're basically having a bunch of dead instructions, and you can't schedule something in that point. But a out-of-order superscalar can attempt to sort of schedule things in there. We can try to schedule non-dependent operations. But our compiler has to come up with some code sequence and has to make them parallel at compile time. OK, so a few questions here. What happens if the if-then-else has many instructions? This was a very simple case here. We just sort of had one thing inside of each of these if-then-elses. It's not the end of the world. What you can do, and typically what people do with partial predication, which is what this gives us, is they'll actually execute both sides of the if statement, interleave them in your VLIW somehow, and then choose the result at the end with a predication or a move z instruction Or these are typically called conditional moves. If you go look in something like x86, I think these are actually called cmove. If you go look in MIPS, it's called movez, but people sort of name these things slightly differently. So it's not the end of the world, but when you go to do that, you're actually going to execute extra instructions that you may not have to have executed. And that's a bummer. Because you could very easily, if there's a lot of code in here and a lot of code in here, and you're executing both code sequences, you're basically doing twice as much work. And if it grows large, you're doing lots of extra work, and you may not have enough open slots to sort of fulfill that. At that point, you have the choice. You actually put a branch in. If it's unbalanced, also not the end of the world. It's probably actually a little bit easier. You're probably not going to execute twice as much code. At some point, though, you may want to actually, if it's super unbalanced, like 1,000 instructions on the one side of the branch and like 2 instructions on the other side of the branch, you may just want to put a branch, an actual branch there, and not try to predicate it. Because if you took the side which only has 2 instruction, or the 2 instruction case, well, all of a sudden you've bloated that by an extra 1,000 instructions kind of in the common case, and that's not very good. So that's partial predication. Let's talk about full predication, which is kind of the extension of that. Instead of just adding a simple instruction which moves data values dependent on another value, it being 0 or not, let's say every single instruction in our instruction sequence, except for maybe, let's say, branches or something like that, can be nullified based on a register. What does this look like? Well, here we have some little bit more complicated piece of code. We have 4 basic blocks. It's roughly an if, then, no, see, if, else, then, and then sort of some code at the end. And let's see how this works with predication. Well, what you can do is, first of all, you have to somehow set the predicate registers. So typically, these architectures have extra registers, which we call predicate registers. The predicate registers get loaded with some values sort of early. And then, let's say this instruction and this instruction execute in parallel. Different notation here. Let's say there's just a semicolon here, and there's sort of brackets around that. And this, in front of the instruction here, in parentheses, we have a predicate register, which says whether this instruction was supposed to execute or not supposed to execute. Now you can do even more complex things than our partial predication. Instead, now you can basically execute everything and not have to do any moves at the end. You don't have to do any bookkeeping, and you can only execute just the sort of side of the branch that you need to execute. Scott Melke in ISCA 95 showed that if you do this and you sort of have a fancy enough compiler, he was working at UIUC on the impact compiler, you can remove, let's say, 50% of your branches. A lot of these branches are sort of short little branches in your programs, and with full predication, you can do some pretty fancy stuff. This showed up in the Plato compiler, which was a HP, or the Plato architecture by HP, and the sort of compiler for that, which was the Wenmei Hu's project at UIUC, the impact compiler. So you can sort of see that you can get a lot of benefit from this. So I'm going to stop here today, but I just wanted to briefly wrap up and say we started talking about how to deal with dynamic events and how to get a lot of the advantages of speculative execution from out-of-order superscalars, but in a statically scheduled regime. And we're going to talk more about how to do some of this code motion, how to move instructions across branches, how to move memory operations across other memory operations. And then we're going to talk about how to deal with some dynamic events, which are hard to deal with in a statically scheduled environment in the next lecture. OK, well, let's stop here for today.